Some are celebrating it with their families. Some are going to nightclubs. You
Say, Rochester, I thought you were going out tonight.
Oh, I am.
Had you better hurry? It's almost midnight.
Boss, on Central Avenue, Father Time lingers till we get rolling.
Really?
Sometimes we roll right into February.
All right, morning to Vorji as well as Celia. Good. You know what? Let's go ahead and start. There's actually nothing more to say except what I said already yesterday. Right? There are a couple changes to the exams. So make sure that you visit channel exam 3 here to figure them out. And today, we'll be breaking open a couple new topics, but they are actually not that unfamiliar because last couple weeks we've been talking about routing algorithms. And today we're going to see how these routing algorithms are implemented into internet routing protocols, okay, and being used by us every day. The first one, more easy, is the lower level routing. That is the routing that's running within the local area network. Okay? And link stake algorithm is very typical, the algorithm being implemented there. That local area routing is also called Inter-Alias Routing. I know. What is AS? Yeah, AS is autonomous system. That is also the first topic today. So, in the next few videos, pretty short, I'll be introducing the term autonomous system and how the intra-AS routing, the lower level routing, interact with the higher level routing, the routing that runs among the local area networks. Okay, so video number 1, an overview of 5.3 and introducing the term anonymous system. Next, we'll be talking about two routing protocols that are actually running on the internet. First is called the Ospf, and it's based on the first principle, the link state routing, the one implements the Dijkstra algorithm. The second, Bgp, is then based on the other routing principle, the distance vector routing. Well, to be exact, Bgp is not just distance vector routing. It's an extension of distance vector routing. It's the path vector routing protocol. And just to tell a little bit more, okay, Ospf is the routing protocol that runs predominantly within a network, a local network. While Bgp, this other one, very, very critical, very, very important, is running on all these backbone routers, okay, all over the internet. Let me take you back to the way we describe these routing algorithms. In that, I introduced the graph abstraction, right? So routers are considered nodes and links considered edges. And therefore, we have a graph where we have edges interconnecting the nodes. So all these nodes, very simple and considered equal. And the graph there you see, the network is completely flat. There's no clear hierarchy. But on the internet, it's so not the case. Okay? So until now, the way we're introducing these routing algorithms is actually very idealized. Okay? Taking a link state routing and put it down to the internet and consider every router as a node, that's not going to scale. Even taking a distance vector routing algorithm, which is already more scalable than link state, if we just put it into the network and having all the routers on the internet implementing distance vector, it will still not scale. Why? Take a look at this. How many possible destinations we might have on the internet if the internet is completely flat? If we draw the graph of the internet, okay, there's going to be how many? Yeah, these many destinations. Therefore, in each of these distance vector routers, in order to store the shortest distance to each of these destinations, in order to store the predecessor, okay, to each of these destinations, how much memory is required? Well, let's say we use 1 byte to represent the shortest distance, 1 byte to represent the predecessor. We'll need 2 bytes, okay, for each destination. And there are these many destinations. If my calculation is correct, this is probably something at the scale of about 8 gigabyte. Yeah, or something like, close to gigabyte. Wow, this is a lot of memory, right? Just to store routing information. And not to mention that we have forwarding tables and all these other things that might be necessary. Yeah, not gonna work very well, right? And if you think about this, hey, this is IPv4 address space. What about IPv6? Ouch, okay, you don't wanna go there. Okay, so even if we use the more scalable routing algorithm, distance vector, okay, consider it working on the internet, not going to scale. Okay? We cannot be storing all destinations. And you know what? Each of these distance vector routers also send distance vectors to the neighboring nodes, and neighboring nodes sending to neighboring nodes. Okay, these distance vector exchange, it's also going to swamp the link, right? Because each of them is this big. You need to send really, really long messages to make sure that the entire 8 gigabyte of this very basic distance vector table gets to the neighbors. Okay. Ouch, and ouches probably. You see, it's not going to work if we treat all routers the same and run just one routing algorithm throughout the internet. It's just not going to scale. Okay. So what we do really on the internet is this. We'll group the routers that are nearby belonging to one organization together as a system, as a local area network. So these are other routers, okay, nearby belonging to another organization, another system. Now each of these systems can work independently. the network admin hired by the organizations could decide independently, autonomously, okay, what routing algorithms they would like. So routers being interconnected in this system can be configured running link state routing. So all the routers running the Dijkstra algorithms. This other system here, okay, the system admin can decide maybe distance vector routing is better, okay, more scalable, better. So all routers here then will be running the distance vector routing. Okay. So systems. What happened on the internet is also this. Each system, the network admin is going to configure, okay, one or two routers and make them the delegate routers. These delegate routers, okay, at the higher level will interconnect. Okay, so this system's delegate routers and this system's delegate routers, they might interconnect. Okay? And there could be lots of these systems around all over the internet. Their delegate routers will interconnect at the higher level in the backbone of the internet. And all these routers in the backbone is going to run one routing algorithm. Okay, so distance vector or link state. Okay. Well, to just tell you ahead of time, okay, for internet, backbone routers run something that's more like the distance vector because it's more scalable because we don't know how many systems eventually the internet will grow into. Okay. So you see two levels of hierarchy. Yeah, there's backbone network, and then each delegate router there associated with it is a local area network. Okay, so internet, again you see here, in terms of routing, is also a network of networks, a network of these autonomous systems. All right, are we awake yet? Okay, good. Next, I'm going to introduce and define better what is intra-AS routing and what is inter-AS routing. And you will see an illustration of inter-AS, intra-AS interplay. And once again, on the internet, we aggregate the routers in a region and call it the autonomous system, an AS. Or sometimes we also call it a domain. So the internet is a network of ASs, a network of domains. The routing protocol within the AS, the network admin configuring all the routers running, is called the intra-AS routing. So you see here, it's the routing protocol running among all the hosts and routers in the same AS. All routers in the same AS will need to run the same intra-AS protocol. Routers, okay, belonging to different ASs can then run different intra-AS protocol. That is an independent, autonomous choice of the network admins individually. Now, each AS will also pick powerful routers, usually sitting at the border, okay, of the AS. These powerful routers, I called them the delegate routers earlier. Yeah, here you see a more formal way of calling them are the gateway routers. Gateway is what? The doorway. Yeah, the router sitting at the border of these AS connecting to another AS. Okay, so gateway routers, powerful delegate routers, will be sitting at the edge, the border, okay, of its own AS and have links both within towards routers within the AS and links to routers in other AS. And therefore, this routing protocol, okay, running in the backbone of the internet is called the Inter-AS Routing. Okay, so that is the routing protocol that's running, okay, across the gateway routers. So this is the routing, okay, working among the ASs, and the gateway router there will be doing the Inter-AS Routing computation. And on the slide here, you see an example of ASs and how ASs interconnect. So we do have three ASs, one here, two here, and three here. You see individual routers interconnected within one AS. Okay, so there are three here for AS2 and three more here for AS3. Now, AS1, 2, 3 each could run its own intra-AS routing, okay? But you see, 1B and 1C. Both of these routers have links internally as well as externally. So 1B and 1C are the gateway routers. So these two gateway routers. Just like 2A for AS2 is one of the gateway routers. 3A for AS3 is one of the gateway routers. Okay. And Inter-Alias Routing is running in between. Okay. 1B, 2A, 1C, 3A, and so on and so forth. Now, the focus of this slide is to talk about how would the forwarding table look like when we have two levels of routing running on the internet. Okay. Now, let me show you an example here. Okay. 1D is one of the routers existing on the internet. What's going to happen there is the forwarding table is not going to be just contributed from the intra-Alias routing algorithm. It would also be contributed from the Inter-Alias routing algorithm. As you see earlier, in order to pass data from one router to another router that's far away, okay, not within the region, right? You need intra-Alias routing to find the gateway router. And you also need the gateway router, okay, to find, hey, where's the destination gateway router? All right, so you do need Inter-Alias routing algorithm telling, okay, each node where to pass data further. Just like you need intra-Alias routing, they're telling you, okay, how to reach another router within the AS. Okay, so forwarding table here will be configured by both intra and inter-Alias routing algorithm. The intra-Alias routing determines the entries, okay, for destinations within the AS, okay, within AS. And inter-Alias, okay, determines entry for the external destinations. To be precise, the Inter-Alias determines which gateway, okay, which router here you should be passing the data to. Okay. But intra-Alias will also be telling 1D here, okay, to go to that particular gateway router, what is the right way? So you see here, interplay of Inter-Alias and intra-Alias routing for packets going outside of the AS. All right. So that is the interplay. Don't worry, there's one more illustration to make sure that the interplay between intra and inter-Alias routing is clear. To make sure the interplay of the intra-Alias and inter-Alias routing is more clear, okay, let's take a step back. Okay. Look at AS1 here, 1A, 1B, 1C, and 1D. Okay, so these routers within AS would run the intra-Alias routing. Therefore, they would know the shortest path going to each other. No problem. Now, at the higher level, at the inter-Alias routing level, so we have these gateway routers. 1C and 1B are the gateway routers of AS1. 3A, obviously a gateway router for AS3. But you see here, 3B having also connectivity to outside to another AS. 3B is also a gateway router for AS3. Similarly, 2A, 2B, 2C all have links to outside to other ASs. So they are also gateway routers. So these gateway routers at the higher level will be running the Inter-Alias routing, so that's another routing protocol, and they will all be running the same routing protocol. They will exchange information to each other using the link state or the distance vector routing to come up with the shortest path. But this time, the shortest path is what? Oh, if I want to go from AS1 to AS2, the shortest path is to go directly from AS1 to AS2. Now, if there's another AS here, AS4, for example, okay, then the shortest path might be to go from AS1, AS2, and then AS4. So these gateway routers will maintain shortest path, but shortest path in terms of, what is the next AS to the destination AS? What is the next AS to the destination network? Okay. So we might have another AS here, AS5. Then the shortest path from AS1 will be what? AS1, AS3, and then AS5. Okay. those said, we may now walk through the scenario here. Let's suppose a router in AS1, say 1D, and it's got packets to go outside of the AS. Let's say AS5 here. Okay. Now, we see the shortest AS path will be the what? A1, AS3, and then AS5. And this information will be available here at the gateway router, 1C, 1B, 3A, 3B. But 1D here as an internal router. So this router here, we'll have actually trouble judging, right? Among the two gateway routers, 1C and 1B, which one of these 1D should be passing the packets to, so that these gateway routers will be able to pass further to the neighboring router along the shortest path to the destination. This is also saying, even though these routers are internal, they participate in intra-AS routing. They do not participate in inter-AS routing, but they need still to know the shortest AS path to these destination ASs out in the world. So 1D, 1A don't do inter-AS routing, but they still need to know the inter-AS path. So they must learn the inter-AS path, which is to know for each destination AS, is it AS2 or AS3 being the next hop AS to the destination AS. And this is essentially the inter-AS routes. And how? Okay, how does 1D and 1A learn? Well, you know what? 1C and 1B do participate in inter-AS routing. So 1C and 1B thereafter, inter-AS routing will then propagate these AS path information to all routers inside AS1. Okay? And so propagation of the AS path, just like computation of the inter-AS path, would also be part of the job of the inter-AS routing. All right, so that was the overview of intra-inter-AS routing. Now, finally, let's take a closer look into the intra-AS routing. And next hour, we'll talk more about the inter-AS routing. This first video is about the options existing intra-AS protocols one may use, a system admin may use. The first big category is the intra-AS routing. Okay, so this is the routing protocol runs on the routers within an AS. It's also known as the Interior Gateway Protocols, IGP. And here, Interior Gateway, not to be mistaken with the gateway routers. So gateway routers are the routers sitting at the border of an AS, having connectivity to other ASs. So gateway router there are to interconnect ASs. But interior gateways are completely internal. And then running on these internal routers within an AS, we have three very well-known protocols. RIP here, not really standing for resting in peace, it's actually Routing Information Protocol. Okay. But if it adds the impression, RIP, this protocol is also the oldest implementation of an intra-AS routing. It came with the Berkeley's BSD distribution. In the 1980s, late 80s. And it's based on this principle, distance vector routing. Yeah, nowadays I'm not quite sure. I don't know if any network admins is running RIP for their intra-AS. But this other one, Ospf, short for Open, Shortest Path First Routing Protocol, this one, on the other hand, is very popular. Okay. So open here stands for open source. Okay. RIP is also open source as it came with the BSD. So it runs also the shortest path first routing. Yeah, you guessed. Yeah, it's the Dijkstra shortest path algorithm that's running. And therefore, it's based on the link state routing principle. And to make sure that we credit the right people, Ospf is actually based on ISIS. It's another routing protocol that was designed maybe 3 decades ago, okay, by early researchers for distributed system research as well as these multiprocessor system research. So in those paradigms, having multiprocessors, if you want to pass the messages around, and these processors are actually forming an interconnected network, you also need to find a path to go from one processor to another processor. Okay, so at the time, okay, those researchers, those computer scientists, have designed ISIS for the purpose. Okay, Ospf for internet, which is also a distributed system. It's just that it's very loosely connected distributed system. Yeah, borrow much of the design principles from ISIS. Third one is called the IGRP, Interior Gateway Routing Protocol. Now, this one is completely closed. It's Cisco proprietary. Okay. It came with these Cisco routers, but it only is maintained until 2016, okay, and obsolete afterwards. The reason for that is because Cisco is also beginning to embrace the idea of doing software-defined networking. Okay, so if you recall, in software-defined networking, routing is all done in the remote controller on the powerful machines. So the routers there, okay, in SDN, pretty much are doing what? Generalized forwarding, okay, and allowing the flow table being installed, and that's pretty much all. Okay, there's no need of running routing algorithms on individual routers. So, starting from 2016, Cisco stopped maintaining IDRIP because there's really no need, very little need of doing routings inside the router. All right, so among all these options, the one that's used more is Ospf. So let's hear more about Ospf. Yeah, let's speak a bit more about the most popular routing protocol here in the Inter-Alias category, the Ospf. Open here stands for, the protocol is open source. Second, the SPF stands for the routing protocol is based on the link state principle. So we do distribute the link state reports all over the network. Therefore, each router will be able to reconstruct the global network topology. From there, then we call the Dijkstra algorithm to compute the shortest path. Be a bit careful though, these routers sending these link state reports, okay, they'll be sending these reports in Ospf message. These Ospf messages are native IP packets, meaning the message itself, and then we append the IP packet header, and that's all. Okay. There's no TCP, UDP, or application layer header on top of that. Yeah, inside these link state advertisements, it's going to contain, hey, who the neighbors are for this router. Also, the cause of the link leading to connecting to these neighboring routers. Again, ISIS routing, this is the predecessor of Ospf, designed by the early distributed system researchers. Now, what we haven't mentioned much yet are these. So these are the advanced features of Ospf. First of all, okay, these Ospf messages, very important link state reports, okay, they can be sent through a secure channel such that the receiver of these link state reports can authenticate, okay, the sources of the sender, therefore preventing malicious attacks. Okay, so yeah, if people can just send these link state reports around, okay, with no security check, one can easily inject a false route, okay, into the system. Second feature is this. One can actually exploit multiple same cost paths. Okay, so in case we come up with the topology such that the Dijkstra give us same cost paths and there are multiple of them, we could actually send data over these multiple same cost paths, which is nice, okay, sometimes. For each link, the metric for the link cost, okay, can be defined also differently for different type of services. Okay, for example, if we are trying to serve best effort traffic, meaning traffic does not require timely delivery, okay, so the receiver can wait longer, then the cost of a satellite link, which the delay is longer, can be set lower, right? Because you would then prefer using the satellite link if the data does not require timely delivery. On the other hand, okay, if the data is real time, okay, then set the satellite link costs high. Therefore, we avoid choosing satellite link along the path to deliver the real-time data. Okay. And oh yeah, it allows also, Ospf allows also integration of the unicast and multicast. Now, if you recall in Dijkstra algorithm, in the end of the algorithm, what we ended up generating is from the source, from the router doing the computation, a shortest path tree. That is also saying that from that source, we could also send a copy of the packet along that tree to all the receiver in the network. So that is also a what? A very efficient flooding tree. Okay, that is a efficient multicast tree. So what multicast meant here is to send from one source to multiple receivers. Okay, so that the extra shortest path tree is also a multicast tree. So from that shortest path tree, we could do unicast, sending from one source to one destination. One can, of course, exploit that to send from one source to multiple destinations. And in the meantime, guaranteeing that it's also the shortest multicast tree. Okay, so multicast Ospf, MOSPF, is a very nice and easy extension of Ospf. Oh, by the way, one can also configure Ospf to run in hierarchy, okay, such as this one here I'm illustrating. So you see, there are two levels of hierarchy here. At the lower level, area 1, area 2, and area 3, okay. Inside each area, we could be running an Ospf, and all these internal routers within an area runs the same Ospf. It requires the same metric, link cost. And then at the higher level, you see, okay, in the backbone of this local area network, in the backbone of this AS, we could have also multiple routers configured. So these are called the backbone routers in general. Okay, some of these backbone routers might be at the border, okay, of the AS. They are also the boundary routers. Some of these backbone routers, okay, are also, okay, the manager of the areas. Okay, so this guy here and here and here are the area border routers. Okay, so the area border routers, boundary routers, as well as the other backbone routers together form the backbone, and they will together run also Ospf, but that is independent of the Ospf running inside each of these areas. So this slide is pretty much repeating what I was just saying. In the example, we do have two levels of hierarchy. Okay, so at the lower level, we have these local areas, and at the higher level, the backbone. Inside each local area, the link state advertisements will only travel within the area. Okay, the link advertisements for the backbone network will be traveling only within the backbone. And each node, okay, in each area is gonna know the entire area's topology. And the node inside an area will only know the direction, okay, to the border area routers in case the destination is outside, okay, of the area. So these area border routers, okay, will summarize the distance to the destinations inside its own area and advertise to the other area border routers. Okay, so that's how the area border routers discover each other at the higher level. Okay, and those advertisements will be shared by also the backbone routers and the boundary router. All right. And that was actually the end of intra-AS routing. You see that the Ospf, it's the most popular probably because it can be easily extended to do multicast. It can also be easily extended to have 2 levels of hierarchy inside a large local area network. Starting from now, we switch gear just one. Okay, yeah, Shanting, having a question. What is Kuro? Okay, so that was the other cat I have that you probably hear in case you pay attention to the video in the background. Okay, so she was meowing there in the background. All right, so we switch topic a little bit to inter-AS routing. And in contrast to intra-AS routings, we do have options, if you recall. RIP, not rest in peace. Ospf, we just hear more. And the EDRIP from Cisco proprietary. Inter-AS routing has only just one protocol, the one and only BGP. Let's get an overview of BGP. Now the second big category, the inter-AS routing. There's in fact just one protocol defining the category, the BGP. Now this is also the routing protocol that runs on all these gateway routers, okay, that are higher in the internet routing hierarchy. Ospf, BRIP, EDRIP, those are the intra-AS routing. So those runs on the regular routers, okay, within an AS. Now, network admin gets to choose one intra-AS routing protocol versus another, okay, as long as all the routers within the AS runs the same routing protocol. Similarly, at the higher level, these gateway routers, okay, in order to find a way to reach each other, they need to run the same routing protocol as well. You see, there's no need of having an alternative, okay, inter-AS routing protocol. Therefore, BGP here is the only inter-AS routing. Very critical. It plays the role of enabling all these packets being exchanged, okay, in the core of the internet. We'll talk more about BGP, but let me share just a little bit ahead of time. BGP here is based on the distance vector routing. To be exact, okay, it's based on the path vector routing. So in distance vector routing, the router tracks for each destination what is the shortest distance and what is the next hop, okay, along the shortest path to the destination. In path vector, okay, so this one running at the inter-AS level, the source AS will track for each destination AS, what is the entire AS level path, inter-AS level path. So that inter-AS level path will contain all the intermediate ASs, okay, along the way from the source AS to the destination AS. So what's nice about keeping track of the entire AS path is this. The source AS knows by default what is the next hop AS. And by counting the number of ASs along the way, you get a rough sense of the path cost as well. But the downside of tracking the entire path is that the memory requirement is higher. But this is okay, right, at the inter-AS level because we try to aggregate destination IP addresses, right, into prefixes. Okay? And if we do that as much as we can, we are not actually storing a big vector containing one entry per IP addresses. Okay? Potentially, we just have a low number of these prefixes, okay, to span the entire IP address space. So, path vector is exactly what BGP, this one and only inter-AS routing, is based on. First line, BGP stands for Border Gateway Protocol, and once again, it is the one and only inter-AS routing protocol that's holding the internet backbone together. To be more precise, it allows each AS the following. First, it allows the gateway router there for the AS to receive subnet reachability information from the neighboring ASs. This is very similar to distance vector. A router receives distance vector, okay, from the neighboring routers. So the gateway routers in the AS receive path vector from the neighboring AS's gateway routers. So by subnet reachability information, we meant the path for each destination subnet for each destination AS. Okay? And there are many of these destination ASs, therefore we receive the path vector, okay, from the gateway routers of the neighboring ASs. Second step, the gateway router receiving such a path vector will then propagate it to all the internal routers, okay, including those routers are gateway routers to other neighboring ASs. Okay. As a result, okay, each of these routers within the AS can calculate what is the best path for a particular destination AS. The calculation can be based on what's provided in the path vector. For example, the path length, right? Or based on the policy of the organization owning the AS. Now, this is more and more likely the case how a router determines what is the best route. Okay? The policy can well be profit-driven, business-driven, security-driven, and things like that. And in the end, when a good AS path is selected for a destination AS, the border router there, okay, then can append, okay, the AS's AS number to the AS path derived, and then further propagate this to the neighboring ASs. Okay, so that completes the cycle of receiving path vector, doing the calculation, and then pass the path vector on to the rest of the internet. And of course, okay, at the beginning, the AS gateway router will announce itself, right? So each AS is potentially a destination. It will announce itself's existence to the rest of the internet. All right, so that's the general idea of BGP and the steps of the BGP working. Now, I'm gonna give you an illustration of BGP routing in a moment. Let me just address Wei You's question here. So Wei You is asking, it'll be a burden for gateway routers, right? Because there will be many packets travel through from AS to AS. Wei You, you are correct. These gateway routers connecting ASs, a lot of times they not only pass data for the users within their network, they might also pass data for the other ASs, right? Choosing this AS as one of the nodes in the AS path. So these gateway routers, therefore, are all more expensive, more resourceful, and the forwarding speed, the switching fabric, tend to be very high-end, high speed. And the routers within a local area network, within an AS, then will be lower end. The routers that are closer to the end users are usually the cheapest. The higher they are in the hierarchy, gradually the highest will be the gateway routers, the more expensive. Okay, so you see that these gateway routers forming the internet backbone, they are typically very expensive routers. All right, so let's let me show you an illustration of BGP routing working. One last point to make is just this: the reachability information, aka the path vector. When they travel across the border, go from one AS to another AS, this is actually part of the exterior BGP protocol. So in exterior BGP protocol, we establish the exterior BGP connections to allow path vectors travel across borders from one AS to another. Now, for path vector that is supposed to be sent internally to all the internal routers, then belongs to the iBGP protocol, and they are sent through the interior BGP connections. And these are actually illustrated using this picture here. Okay, so if we focus on AS2, we do have two gateway routers, 2A and 2C. So you see these gateway routers connecting to other ASs. Yeah, there are exterior BGP connections to outside. Exterior BGP connections to outside. So eBGP, yeah, in red color. But in addition to that, 2N and 2C both need to send path vectors internally. Okay, so you see they went through the iBGP connections. Alright, so iBGP connections in blue. So once again, these are gateway routers, and the gateway routers you see having both the red connections and the blue connections. Yeah, they run both the eBGP part of the protocol as well as the iBGP part of the big BGP protocol. Those BGP connections are often referred to as the Bgp sessions. So these routers will exchange messages over semi-permanent connections. Yeah, the reason that they're called session is probably because it's semi-permanent, so it's on all the time, and occasionally you take it down and then restart it. Okay, so semi-permanent TCP connections. Now, TCP. BGP is a routing protocol, right? These messages we send should be at the layer 3, but TCP is actually a layer 4 protocol. Okay, how do you like this? On the other hand, TCP allows reliable data transfer. So would you prefer the path vector? So these messages that we're exchanging between the BGP routers, the path vector is being sent reliably or not? Yeah, to push it a bit further, what about using TLS, okay, the secure version of TCP? If we use TLS, these BGP messages, these path vectors, would look more like an application level message. So you think about it, you debate within yourself. Now, the messages we're exchanging between the BGP routers over the BGP sessions are these. Yeah, the paths to all sorts of destination networks, the paths to all sorts of destination ASs. In fact, yeah, altogether, we just call it the path vector. So BGP, again, a path vector protocol. And let me give you an example here. So let's say in AS3, okay, there is a prefix X, okay, and this is the destination for packets coming from maybe AS1 or AS2. So AS3 that learns about this destination will need to announce, okay, advertise it to outside of AS3. So 3A here, okay, will need to announce, okay, its existence, and pending its own AS number, so AS3 here. So this will be the AS path, okay, being advertised. This will be the AS path being sent in the BGP message to the other end of the exterior BGP connection, to the other end of the BGP session. So 2C here, okay, will receive the AS path, AS3, X. So AS3's gateway router 3A will advertise the path to AS2's gateway router 2C. So when AS3 does this, it's also saying that AS3 promises AS2 to relay packet, okay, on behalf of AS2 so that it can reach destination X. All right, so that was a quick overview of BGP. We'll talk more in detail after taking a break. Because in the first hour, we don't really have any quizzes. I guess that you guys might be experiencing a little bit of video fatigue already. So let's take the break earlier. Okay, because the next hour, there will be some 30 minutes worth of video, but there will be a series of quizzes coming. Okay, talking about BGP doing routing based on policies more these days than the path lengths. So let's break now. Currently, I have here 11:06. Let's resume the lecture 11:16.
Come on, Mary, how about a glass of eggnog?
Oh, sure, Jack. Wait a minute. Who made that eggnog?
Rochester.
Uh-uh.
Why, what's the matter?
Well, last New Year's, I tasted some of Rochester's eggnog, and the next thing I knew, I was at the Rose
This is New Year's Eve, bub. I gotta keep rolling. Wanna have a quick one with me, Phil? Down up. Step aside, kid.
All right, so I don't know if you have time to think about whether you would like to use TCP connection to send routing messages, such as the ASPass advertisements. So let me know if you don't feel comfortable doing that. And try to recall what is wrong with that? I think we talk about that when we talk about NAT, I think, right? We mentioned that it's actually violating the end-to-end argument, where we begin to lose this modularization we are enjoying designing the Internet Protocol stack, right? So using TCP to transmit the ASPass is probably not a good thing, because you kind of depend on a protocol at the higher level for a lower level functionality, because routing is there to ensure that we can connect at the first place. Yeah, so this is probably not something that's really nice to do. Okay, but having TCP implemented already, it seems quite convenient just to establish a TCP connection from gateway router to another gateway router where you know the IP address. So these TCP connections are actually manually established. There's no discovering process. And the fact is that more and more these days that system admins are probably doing TLS. This is so that we avoid people injecting false ASPass advertisements into our domain and causing troubles. Because one can actually inject false ASPass advertisements and then drawing traffic they are not supposed to see. Yeah, very interesting how the internet is growingly more human, okay, more political. You will hear more. But now let's come back to the BGP overview. There's one thing that I missed talking about, which is the message exchange. Okay, so here's the video about BGP advertisements exchange and message exchange. What are the message formats? Let's say more about the messages we exchange in these BGP sessions. So these messages are essentially pass vectors. Inside the pass vector, we have lots of these pass entries, okay, or route entries. Each pass in the pass vector of BGP is this: the destination address. Now, because in BGP, we are sending packets to a destination network. Therefore, to address to a destination network, we use the prefix of the destination network. And then attributes. Now, in pass vector, the most important information there is the path. Therefore, you see, Okay, in the set of attribute here, we need to definitely have the AS pass. So AS pass is the most important component in the set of attributes. There we see the list of ASs. Okay, it takes from the source to reach the destination. The discovery of the list of ASs, the discovery of the AS pass, however, okay, came the other way, from the destination network. Okay, so the destination network is going to advertise its prefix, okay, and so that's going to be in a advertisement message. Okay, so the home AS of the network X, okay, let's say AS2, okay, receiving such an advertisement at the gateway router. Okay, that gateway router is going to prepend itself. Okay, prepend the AS number. Okay, AS number 3. Okay, before X, and send this out as the prefix advertisement to the neighboring AS. The neighboring AS, let's say AS2 there, receiving such an advertisement, it's going to prepend itself before it sends out further to AS2's neighboring AS. Okay. So now AS2's neighboring AS receiving such an advertisement will then discover a path to go from AS2, AS3 to destination X. Okay. So list of ASs through these paths, the prefix advertisements as traversed. Okay. So that is the AS path. One and the most important part in the attribute set. Second important is this, the next hop. Now this is not quite the next hop AS, the next AS number in the AS path. No, it is actually the gateway router within the source AS that is directly connected to the next hop AS. So it's carrying the IP address of the gateway router, leading to the next hop AS. So the two together necessary forming the attribute set. Now, BGP routing has grown more and more being policy-based, meaning the gateway router, they're receiving these prefix advertisements. It's not like for every advertisements they will actually prepend its own AS and then pass it down further to other neighboring ASs. There'll be some sort of import policy. So the gateway there receiving the advertisements will have to say, will have to decide. Some of the advertisements they will decline, and some others they accept. Only the ones they accept will be propagated further to all the routers within the AS. Now the gateway routers in the AS receiving these accepted advertisements will then decide whether to prepend themselves and then pass the expanded advertisements to the other neighboring ASs. But you see, there are also policy the AS might apply before these other gateway routers advertise the expanded AS path to the neighboring ASs. So some of them actually might have complex policy that is very fine-grained. For example, if one gateway router connects to two other neighboring ASs, this gateway router might say, I send this particular extended advertisements only to one of the ASs. Policy to import and policy also to export. All right, and now let's take a look at an example. Let's go over a couple more examples so it's more clear where the import policy and the export policies are applied. So this is the same example we saw earlier. Destination network is here, X, and so AS3 there is gonna send the pass advertisement. That looks like this: AS3, X, and this is gonna reach 2C of AS2. So AS2's router 2C receives pass advertisements like this. And this is through the exterior BGP connection. And the advertisement came from AS3 and from router 3A. So 3A of AS3. Now, yeah, if you recall in the very early slide, right? The border router here would then propagate the AS path throughout all routers in the network. But no, there's import policy. So yeah, the exact process is more like this. 2C there will actually check AS2's import policy. If the policy says 2C, it's okay to accept the pass, then 2C propagates the pass to all routers internal of AS2. So sending of these AS paths internally is through the interior BGP connections. All right, so the import policy actually happens before the propagation of the paths, okay, to all the routers internally. And then, 2A here, receiving such a pass, can then prepend itself and pass it further to the neighboring ASs. But wait, yeah, the export policy is applied here before passing on of the advertisements. Yeah, that's check. If 2A here is allowed to advertise the discovered pass to AS1 here, okay, then we form the new advertisement AS2, AS3, and X, and then send it to 1C that belongs to AS1. Okay, so once again, before the prepended, the extended AS pass can be advertised further to the rest of the internet, we check the export policy. Right? Second example is a bit more realistic. So 3A here, the gateway router of AS3 might have multiple eBGP connections to outside. Okay, so in that case, a gateway router might learn multiple paths to a destination in AS3. So let's see. One of the paths is this, right? AS3's 3A sends AS3X, okay, as an advertisement to 2C. 2C checks the import policy and therefore pass it on to all the routers internally. 2A picks it up, checks the export policy, and let's say that it's just allowing advertisements of the pass further. So prepend AS2 to the pass and then send it further. At this point, 1C learns the pass AS2, AS3 to destination X. And the way to go is for 1C to send to 2A. The other direction is this. 3A can be simply sending what? AS3X, okay, this past advertisements directly to 1C. And 1C will just simply learn, right? There's another way to reach destination X, which is just simply sending it to AS3 through 3A. Okay, so these are the gateway border routers that 1C send the packets to, okay, for the two different paths, 2A and 3A. At this point, 1C sees two advertisements coming in. Yeah, before 1C propagates any of the paths further, okay, it needs to check the import policy. Okay, so AS1's gateway router 1C there, it will need to choose. It could choose one of the two, or it could just take both of them. Okay, let's say that 1C chooses AS3, X, yeah, sure, the shortest AS path, and advertise it to all routers internally of AS1. Okay. This is the second. Right, so that was the second example. The next section of videos, just to tell a little bit more, because we have not yet talked about the details of how BGP interact with Inter-Alias Routing, such as an Ospf. And here's the beginning. Let me borrow example 2 here and continue to talk about this. how a router sets up a forwarding table entry, okay, for a destination outside of the AS. Okay. Yeah, scenario the same, destination being X. 3A, the gateway router of AS3 has 2 eBGP connection, therefore 1C here potentially can receive 2 AS paths. And 1C, according to example 2, chooses the shorter AS paths. So let me run the animation. So 1C discovers 2 paths and picks the shorter paths. Okay. And this shorter path is further propagated internally to all routers. So 1A, 1B, and 1D will learn about the shortest path to destination X from 1C. And what 1A, 1B, and 1D will do is, well, if I receive ever any packets with destination X, then I will forward the packet towards 1C. The border router, okay, they receive, okay, the AS path from. To make it easier to explain what's coming up next, let me just label, okay, for 1A, if the packet is supposed to go out on this interface, then we call that interface 1. And yeah, for packets to go out on this other interface, let's call it 2. Okay, similarly for 1D, this is interface 1, this is interface 2. Now, 1D here, okay, has discovered there is a path to destination X that is going through 1C. Okay, that is what 1D knows so far. To add an entry into the forwarding table for X, 1D needs to know exactly which interface, is it 1 or 2, that leads to 1C. How would 1D know that? Call the Inter-Alias Routing there. Okay, let's say it's Ospf. So Ospf is going to tell us if the destination is 1C, what is the link, okay, along the shortest path to 1C. Okay, so that happens to be 1, so we will fill this entry here, okay, interface column being 1. Similarly, let's try to derive again for 1A. Okay, so 1A knows, for destination X, I should be forwarding packet towards router 1C. So let's call Inter-Alias Routing and find out from Ospf, what is the shortest path to 1C and which link, is it 1 or 2 on the shortest path? And we'll get 2 here, and 2 here would forward packets to 1D, and 1D here we see earlier will be forwarding packets over this direction and reaching 1C. Therefore, going backwards and reaching destination X. All right, so that should give you a little bit more detail exactly how BGP works. There are just 2 short videos, one specifically talking about the routing protocol and the message format. Route selection. Now, this mechanism is necessary for slightly more complicated scenarios. Let's go back to example 2 again, right? We have this router, 1C, being the gateway router of AS1. So you see towards the end of the scenario, AS1 discovers 2 AS paths, one from AS3 to go to destination X, the other from AS2, and then via AS3 to go to destination X. So in the previous slide, we say the policy of AS1 is such that we only select this to import. And so 1C propagates this AS path to all internal routers. Internal routers will then send packets, destination being X, through 1C and therefore being forwarded to AS3. Very simple. But what if we relax the import policy a little bit further so that 1C here cannot discard this other AS path? As a result, 1C will need to propagate both paths internally. So each of these routers internally will see more than one route to the destination X. Ouch. Yeah, so that's when we apply the route selection. So internal router there will need to apply route selection here to decide which of these two, okay, it will send packets to. The process is like this. Step number 1, check the local preference of these routes. So if you recall earlier, a route, okay, is what? Composed of the destination network's prefix and a set of these attributes. So we know that ASPass is one attribute. Next hop is one attribute. There's one more attribute called the local preference. Okay, so this one actually weighs the highest. Okay, so BGP actually checks the local preference first and take the pass with the highest local preference. Okay, so local preference there is usually to indicate, yeah, between the two neighboring ASs, AS3 versus AS2. Does AS1 prefer forwarding packets to AS3 or AS2? So if AS3 is preferred, AS3's pass, so this guy here is going to carry a higher local preference. Okay. Now, if there's no local preference specified, then we go to step 2. So the internal router, let's say 1D here, okay, will then check which of these multiple paths to destination X give us the shortest ASPass. So in the scenario, 1D is going to pick this one. Okay. Now, if both ASPass have the same path lengths, then we go to step 3. We pick the closest next hop router. Okay. Yeah, 1D here sees 2 paths. Okay. The next hop router for this path is going to be 1C. The next hop router for this path here is going to be 1C as well, because 1C is the border router, okay, receiving, okay, these advertisements. But if you consider, okay, a slightly different scenario, okay, so again, we have AS3, AS2, and AS1. Okay. And okay, so the router now in the limma is now 2D. 2D here actually sees 2 ASPass. One ASPass is actually coming from 2C. 2C is the gateway router connecting to AS3, okay, which it receives a pass to X, AS3, X. 2A is the gateway router connecting to AS1, where AS1 is passing another ASPass, okay, to AS2. That is AS1, AS3, and X. So 2A pass this pass to 2D. 2C also pass on this pass to 2D. Okay, so 2D in the end learns, okay, there's one ASPass through next hop to A, this guy. There's another ASPass through 2C, this one. 2D here, okay, assuming that abandon the shortest ASPass phase, goes straight to the closest next hop router phase. Then we'll do this. For this pass, next hop router is 2A. For this pass, next hop router is 2C. 2D here will consult, okay, the intra-AS routing again to find out, is 2A closer or 2C being closer. So if you see the scenario, 2A distance to 2D is only the link cost between 2A to D, which is 201. Distance between 2D to C, however, is 263. So 2D here is going to choose 2A to forward the packets to. So it's going to choose AS1, AS3, and X, this other ASPass, which is actually longer, okay, than this other one to pass the data. This is also very well known as the hot potato routing. Allow me to explain. Yeah, so 2D is this guy holding a hot potato. So Yeah, the packets are almost like these hot potatoes, and 2D can't wait to get rid of these packets. So 2D wants to be able to pass the hot potatoes, the packets, as soon as possible. Therefore, picking this poor guy here, 2A, to throw all the hot potatoes over. Okay, distance is shorter. Okay. All right, how do you like that? You see, once again in BGP, there are, one more weird design. So inside the router, intra the local area network, okay, although the router knows that there are multiple AS paths to the same destination, it's not necessarily choosing the shortest AS path. It's actually choosing the gateway router that is closer to the router, so that the router can hand the data over faster. Okay. So on the internet, you see a lot of times the routes are not always the shortest AS path routes. Okay. But there's a good reason for that, because eventually internet engineers discover also that a shorter AS path does not mean shorter delay paths either. Because you might go through an AS that's huge. The internal network is huge, right? To traverse through just that one AS, it could take a lot of time. So a shorter AS path on the internet, unfortunately, does not equate to shorter delay. Knowing that, internet engineers begin to come up with these weird ideas. For example, hot potato routing, in that an internal router will throw the packet to the nearest gateway knowing there is a path to the destination and care less about the AS path length. Oh, Yanjun has another question. Isn't the priority of... Hey, Yanjun, you're asking the right question. I knew you guys are going to ask, hey, how come, right? Shouldn't be the shorter AS path the better? It is not quite. A lot of times, shorter AS paths, not necessarily shorter delay. And not necessarily better available bandwidth either. So a shorter AS path doesn't tell all that much about the performance metrics, okay, of the path. Good question, Yanjun. And I have not yet shown the video about the BGP messages. Now, this is pretty short. This is the last slide of the BGP protocol. Okay, so in BGP, the protocol, it actually defines 4 types of messages. Okay, so not just the message we mentioned earlier, containing the path vector being passed in the Bgp sessions. There are other types of messages that BGP sends. So some of them are actually to send the path advertisements, to send the path vectors, but some of them are to establish the TCP connections, okay, for the session, or to tear down the TCP connection, or to keep the TCP sessions alive. Okay, let's go through these BGP messages. The first type is called the open message. Yeah, the first purpose of it is to establish the TCP connection. Okay, so the sending peer there will be sending an open message to the receiving peer. Okay. Receiving peer will be sending back an ACK for that message. As a result, the 2 peers establish a BGP session. So the ACK of the open message there is going to be in the keep alive message format. Okay, I know it's a bit tricky. Now, the open message is also used to do the authentication. Okay, so the 2 peers can authenticate each other to make sure that the path advertisements, okay, are indeed the true paths, okay, to be discovered. Now, update message. So this is the message being used to send the path advertisements, the path vectors. So this message is also allowing the routers to withdraw outdated path vectors. Keep alive message we saw earlier, it's to ACK the open message to establish a TCP connection. Oops. This is the last slide of the pass, okay, which being used to set the pass advertisements, the pass factors. So this message is also allowing the routers to withdraw outdated pass factors. Keep alive message we saw earlier, it's to act the open message to establish a TCP connection. Keep alive message is also being sent, okay, periodically to refresh the TCP connection, just in case there's no update messages being generated. So update messages is the pass advertisements. Last is the notification message. Okay, so this reports in case there's any error in the previous message. Okay, and it's also used to close the connections for the peers. All right, so those are the 4 kinds of messages defined in BGP, mainly to establish connections and checking whether the connection is in good health. Yeah, so Yanjun was saying that, hey, I thought the order is listed because of the pass lengths. You know what? You are also right, Yanjun. Okay, those ordering, the route selection, those are actually for the border routers, the gateway routers to decide how to import an advertisement and how to export the advertisements. But that hot potato routing we're talking about is actually for an internal router to decide if there are data going to a specific destination. Yeah. So that decision from internal routers are actually not considering shorter AS pass. Okay. So for example, a gateway router seeing multiple AS advertisements coming in, that gateway router can choose the shorter AS pass to propagate internally as well as to the other gateway routers. So these other gateway routers will only advertise a shorter path to the destination to the yet neighboring ASs. Yeah. You see, that route selection policy there, route selection rules there, is still working, but working more at the importing side, exporting side. So export gateway routers might also see from multiple gateways within the local area network saying, hey, these are taken and allowed, but the exporting gateway router can use also the same route selection priority to decide maybe we just advertise out the shortest AS pass in the BGP announcements, BGP advertisements. Okay, so there are actually 2 levels of things. The gateway routers are trying to discover AS pass. And then there's internal routers trying to send actual data. Okay, these internal routers, they do not participate in the AS pass advertisements. All right, I hope that cleared the confusion a little bit. Next video, this one is very critical because it will set the stage for the quiz series coming ahead. Bgp policy. One very important issue about BGP to discuss here is, BGP routing is very policy-based these days. If you recall, there's import policy, there's export policy, there's also local preference for route selection. There are lots of things the network admins can tweak, to decide where packet goes. The reason for those policy-based setting is this. Let me use an example to explain. Consider this network. We have 3 ISPs in the middle, A, B, C. They are the provider networks. W, X, Y are the customer networks. More specifically, W is the customer of ISP A. So W pays a some amount of money every month, and A will in turn help W passing packets, going out to the rest of the internet or coming in from the internet. Similarly, if the traffic is as opposed to go out the other direction. All right. So W pays A, and therefore A is responsible to serve W. Similarly, for this customer-provider pair, Y being a customer, C being a provider, X being a customer, B being a provider. Now, X is a little bit more complicated. It's multi-homed, okay, customer network. So X here pays B and C. Okay, as a result, B and C should both be forwarding packets for X. In scenario 1, let's assume that there's a user in customer network Y here wanting to send something to the user in W. And so in order for W to draw in traffic from the internet, its provider A here will need to announce its existence. So AW here, okay, an AS pass needs to be sent to the neighboring ASs, which happen to be ISP B and ISP C. Okay, so A advertises pass AW to B and to C. As a result, okay, B is going to see this pass, okay, and prepend itself, okay, and see if this AS pass needs to be further advertised to yet another neighboring AS, such as provider C. Now, B's network admin actually knows better and chooses not to do that. And the reason for that is because of this. If BAW is advertised to C, C is going to discover, this is actually one way for this user in Y to send traffic to user in W. And therefore, the traffic is going to go this way to W. And you know what? B here, okay, B does have a customer X. X is paying B. But is W paying B? Is A paying B? Is C paying B? Well, based on the setup of the problem, WAC not paying B, and yet B is using the network resource here to transit the traffic for B and C. Okay, so B gets no revenue to do this route, BCAW. Because CAW, based on the scenario setup, not paying B. Okay. So, chooses not to advertise BAW to C is so that C does not discover this pass. And therefore, okay, not using this pass to send traffic. Instead, C here receiving AW is going to prepend itself, CAW, and Y is going to use CAW as a way to send traffic to the user in W. So you see in this scenario, very obvious. For a customer network, ISP will be happy to route traffic to and from the customer. Okay. But the ISP not getting paid by others would hate to transit traffic between these other ISPs. Okay. So bottom line, not getting paid for the work. Scenario 2 is very similar to scenario 1. The network is completely the same, and we just continue scenario 1 from here. When B has discovered BAW is a pass to go from B to W. Now back in scenario 1, admin of B chooses to not forward BAW to C, okay, so that we don't draw traffic this way. Nice. But B will actually have to send BAW to X. So X can discover XBAW is a pass. So just in case there's any user in X wanting to send data to user in W. Nice. So makes sense. But hey, X is dual home, so there's yet another connection to a neighboring ASC. So should the network admin of X here send XBAW to C? Well, that's let's assume that we send XBAW to C. In this case, C is going to discover CXBAW is a path to send data to W. Similarly, Y is going to discover YCXBAW is a path to send traffic. YCXBAW is a path to send traffic from a user in Y to a user in W. And that's going to travel like this. How do you like this? Well, from an access network admin's point of view, hey, this traffic is actually not for me at all, right? It's actually between Y and W. Y pays C, W pays A, and no one is paying me, and yet I'm paying B and C. Okay, so it's a big no-no for X here to send XBAW to C. All right, so X will not want traffic coming from C and simply transiting to B. So X should not be advertising anything to C, okay, coming from B. So again, money is the issue, all right? So X is not getting any money from C or from B. Therefore, X is not happy transiting traffic for these other ISPs or even from other customer networks not paying. Okay. All right. So on the internet, routing is really a business. And let me try to make sure that it's very clear to you through a series of quizzes. Quiz number 45, this one is the straightforward one. And let me try to explain the network here. Oops. Okay, 1 second. Okay. So quiz 45, let me try to explain the scenario. So we do have a network. Neither BX, definitely. Yanjun, you are right. So come back to quiz 45. We do have a network here. Okay. The legend is similar to the example we saw in the video. A, B, C. Okay, the bigger irregular shapes are the provider networks. And smaller circles, X, Y, and W, these are customer networks. Okay. And we do have Y here wanting to send data constantly to X. All right. A little bit more background. So X is the customer of B, so X pays B. B, being the provider, needs to ensure that the traffic, okay, coming into X or out from X should all be forwarded. Okay, so B is responsible for forwarding traffic from X as well as to X. Okay, Q1 asks, should B advertise the AS pass BX to A? So where's B? B is here. Okay, there's a AS pass BX. Because destination is X, right? So X will need to announce its existence to B, and that's when B discover BX is a pass to X. Okay. Now B here needs to decide whether to advertise the AS pass BX to A. Okay, A is the only neighboring router. This is a tree network. So for Q1, do you think yes or no? Okay, and for either case, tell why. Q2, let's suppose B advertise BX to A. Then A will discover what? ABX is a way to reach X. So should A advertise the pass to C further? Yes or no? And why? All right. And you know what? I've actually seen some teams answering. Oh, cool. Okay. So team 4 is saying yes. Okay, for Q1, yes, since B4 traffic from X. Yeah, in order to draw in traffic from Y, definitely B need to tell BX to A. Should A advertise ABX to C? Yeah, Chunmao, Team 4 was paying attention to the video, right? A was not paid by B, A was not paid by C. So A says, no, I'm not gonna advertise that route further to C because I don't get revenue. Yeah, so if the only traffic that's gonna go out is just the only traffic that's gonna go through the network is just Y to X. Yeah, looking at the revenue, dollar sign, I think Q2 for me is also false. A should not be doing that. But should A advertise BX to W? That will probably be okay, right? Because that would ensure W, A's customer, to send traffic out to X. Oh, Team A, Jessica is saying yes and no. And Yanjun, okay, sure. So in case A is really nice, yeah, then yes, A sends advertisement ABX to C. Okay. All right, I think you guys kind of get the idea. Okay, let's look at, but okay, there's a caveat though. You see that, hey, C here might connect to other providers and other customers. And chances also high that A might be a critical point that connects two major parts of the internet. Okay, in such a case, okay, A might not be nice, but A might be pressured. Sorry, did I mention that internet routing is also a little bit political? Yeah, A might be pressured into sending ABX to C as well. All right, so that was quiz 45. I think you guys are getting a hang of it. Let me see. Team 5, yes and no. Yeah, based on revenue, yes and no. Very good. Some of you might say yes, because for the second, for Q2, yes is just for the sake of the internet being connected. Because if A there being a critical point connecting the B part and the C part, and A did not announce ABX out to C, the C part will not see X at all, B at all. That is saying, hey, didn't we say that we want to send data from where? From Y to X. Internet is physically connected, but there's no route because A says, hey, no. It's a little bit like, sorry, I don't know how to say it in English, right? There was this novel I read when I was in childhood called 水浒传. 此路是我开，此树是我栽。若要从此路过，留下买路财。I'm not sure if I'm saying it right, but hey, that's the idea. So if A wants to bully the internet, A is definitely in the position to do so. And that's also partly you see that the internet backbone nowadays are growingly more redundantly connected. Oh, okay, thank you. Totally, more redundantly connected. So each ISP try to ensure they have multiple connections to other ISPs. Okay, so you see, it's internet can be very interesting this way. Okay, and let's move on to quiz 46. All right. Yeah, that's why BGP is a little bit harder to understand, because it's as complex as human network, social network. All right. Even though distance vector, hey, you thought Bellman-Ford and good new travel fast, bad new travel slow is already hard. But actual BGP routes a lot more complex. All right. Yeah, so let's now look at quiz 46. Okay, if you are keen in observing the graph, you see that, hey, the two networks are a little bit different. Okay, in this case, we have a cyclic network, so there's a connection between B and C. Hey, let's try to make the backbone a little bit better connected. All right, so this scenario is a little bit more realistic. Okay, so everything else is the same. And now Q1 asks, oops, let me clear the mark. Q1 is asking, A and C charges B. So A and C charges B. And A and C charge B the equal amount of money to forward data to and from B. Okay, so C says, I'm going to charge you this much to forward in or out. A says, hey, let me charge you the same amount of money, okay, per unit, in and out for you. All right. So in a way, A and C, although both ISPs and B ISP, but A and C are actually higher level ISPs, okay, bigger ISPs, serving the other ISP B. So B is actually maybe a newcomer into this ISP business. So B actually pays A and C for connectivity to the rest of the internet. All right. So this is yet another precondition. Suppose you are now hired by B. Okay. So, hey, you are hired by this new ISP. Should you advertise BX to only A, only A, or only C, or both of them, or at least one of the two? And why? Okay. You see here, it's a little bit open, right? Because they cost the same. So you pick one of the two, or both, or at least one of the two. Okay. So tell me which one you choose and why. Q2 over here, change the scenario a little bit. A and C are charging B, but C charges A more, while A charges B less. So it looks a little bit like this. So this indicates the money flow. Okay, so the brown arrows indicates the money flow. Again, you are hired by B. Would you advertise BX to only A, only C, both of them, or at least one of the two, and why? All right, so that was, okay. That was 46. I think you guys have already, tried to respond. Okay, so team 4 is saying, okay, in case the costs are the same, right? B sent to both. No difference. So whether the traffic is coming from A or coming from C to B, no difference. All right. Okay. If B only sends one of them, then the traffic will not be in balance. Okay. So maybe most of the traffic will be stuck in one of the ISPs. So in terms of trying to make sure that the internet is somewhat balanced in traffic load, okay, good argument not to send to just one of them. Okay. Advertise to only C because C can afford more traffic. Yeah, okay. Yeah, okay. So, but you see that in this case, right, if B forwards BX to C only, traffic will only be coming from C, and B will then be paying more for the same amount of traffic. Isn't it, Wei Yao? And I think Chunmao is probably trying to add, right? We don't know whether A and C is connected. Oh, okay, interesting. Sending to both because you don't know if A and C are connected. Q2, I think it's still both with the same reason of Q1. I see. Okay, the other, an alternative solution for Q2 is sending BX to both A and see which one will be forwarding traffic. I think Chunmao is thinking that there might be traffic coming not just from Y, right? If there are traffic not just coming from Y, which is a customer of C, you definitely need to make sure that A also know about the path. So W can send traffic to X. I think Chunmao, you are right. All right. Okay. But guys, think a little bit more. In case the only traffic we need to forward is just Y to X, and we do know that there's a connection between A and C. Right. If you do want to save money for B, ISP B, what are you gonna do? So if I'm being hired by B, probably will only advertise to A, BX, okay, and drawing traffic only from A. Okay, but again, that's assuming that I know there's a connection between A, C already. All right, Team 15, very good quick reacting. Yeah. Okay, I guess you guys have already get the point of quiz 46 there. Of course, if you think about random customers on the internet wants to send data to X, yeah, it would be better for B to advertise BX to both ends. And why don't we move to quiz 47? Okay, allow me to go a little bit faster so that we could get to the final point. Quiz 47, it's actually very similar to 46, okay? Network identical, all right? And we know already, B advertised BX to A and C both. A advertises further ABX to C because A here, after receiving BX from B, can append itself ABX and then send that to C. C at this point will know, hey, there are two paths to reach X. So there's BX coming this way and then ABX coming the other way. All right, let's assume C charges A more and charges B less to forward traffic. Ooh, okay. C charges A more, okay, to forward traffic, and charges B less to forward traffic. Okay, so C is a super ISP charging both the neighboring ISPs for money to forward traffic. Suppose now you're hired by C. would you advertise CABX or CBX or both to your customer network Y and Y? Okay. Think again this time. We have just traffic from Y to X. C here, would it be advertising BX or ABX? In case, trying to maximize dollar signs. Oh, I see. Yeah, so Team A, you've got it. Yeah, in order to maximize profit, definitely CABX, right? Because then Y will be forwarding traffic to, of course, C, and then A, and then B, and then X. And C can get more money from A. Internet is such a weird world. Yeah, so ISP is not a very easy business to do if you're starting up your own. You're always paying people for internet connectivity, whether you are getting data from them or asking them to forward data for you. Very good. And that takes us to the final quiz. Oops. All right, so final quiz. Again, scenario is continuing from 47, quiz 47. Okay, and the point I want to make is it's really a money game. Okay, internet is policy based. It's sometimes based on money, sometimes based on politics, and sometimes business competition. All right, so this is the ultimate case. And this is to illustrate that A could be in trouble. Okay, so let's continue from quiz 47 and consider CABX is the path, okay, to send traffic from Y to X already. Okay, so the only new condition we are adding is this: C charges B more than A charges B to forward traffic. Oh, so we know from quiz 47, C is charging A more and B less, forwarding traffic for A and B. You know what? A and B also has a certain paying relationship. And here, C charges B more than A charges B. So that is saying, hey, there's one more brown arrow indicating the money flow. Okay, and A is charging B less than C charging B. So the error is even thinner. Now, suppose you're hired by A. You find, hey, this is so unfair, isn't it? Right? You get very, very little money from B to forward the traffic, and you pay C a lot of money to forward the traffic. Ouch. Would you raise or lower the price charging B? Why? Would you raise or lower the price paying C? Why? And business negotiation is not always easy to do. Could you think of other solution so that you can bypass negotiating the prices you're paying or charging people? You know what? As someone who take Introduction to Computer Network and studying BGP, maybe there's some trick you can play. Okay, when you are advertising the BGP pass out to the other ISPs. Okay, so A is a domain, you see. A can also decide a certain export policy, certain import policy, isn't it? Okay, in case B is not willing to pay more, in case C is not willing to lower the price. So let's see. Okay, I see some team also try to address quiz 48. Team 4, raising. Obviously, you need to charge C more, definitely. I'm sorry, charging B more, definitely. And ask C to charge less. Q3 thinking, okay, sure. Team 4 still thinking. All right, so a little bit of hint here, okay? If I am working for A as a system admin, and the traffic I observe coming from C always go out to B, then maybe the next hour I start forwarding the announcement ABX to C. Then that way I will be able to negotiate with C better. Hey, charge me less because you have data that you want to go through me. Okay, I guess team 4 here for Q3 is calling out for help. Okay, very interesting. Yeah, add Yo Wei Yo. Yeah, Wei Yo. Can you help Chimao out here? Any other solution? Yeah, it's actually okay to have none, so you could stick to doing business negotiation. Okay, but a lot of times, in order to negotiate effectively, you've got to know the weaknesses of your opponents. Okay, so in this case, the weakness is that they do need to transmit traffic to X. To X. So why customer of C does need to transmit packets to X. All right. Guys, you know what? That's pretty much all the time we have, and it's already overboard. We're supposed to end 10 minutes earlier. All right. Okay, so with that, let me conclude. This is the end of the semester. I'll see you next year, okay, during the exam. Feel free to stick around if you have other questions or try to complete quiz 45 to 48. And these are due on Saturday. Oh, and by the way, thank you all for the patience throughout the semester. Okay, this is also the last lecture. Thank you to Bing Rui for reminding me that. And then we go off to the music play. Oh, thank you. Yeah, I guess you guys figured it out. But I also discovered that over the years, I cannot be too nice. Being a teacher, I also need to be firm. All right. So I try to be nice, but I also need to, hold on to the rules, hold on to the grading policies. Oh, thank you. Thank you all. Thank you, Shanting. Yeah, thank you, Min Hong. Shu Quan, thank you. And I think Boris and Chuma. Also, Eximan, I think you are Sheng Wei. Thank you, Wei Yao.
Up another year. 1953 is just about finished.
Yeah, and me too. Hey, I wonder what happened to all the things I was going to do in 1953.
I don't know, but that's a familiar question.
Remember, I was going to give up smoking, be more polite to people, read some good books, and all stuff like that there.
I remember.
Well, it's sure great to have a whole, fresh, brand new year to do them things in. Remind me, will you?
Let us all sing a song today, sing it out loud and hard. Maybe we won't be here this way 100 years from now. Let us all dance around a while, learn a new step somehow. Maybe we won't be here to smile 100 years from now. Let it rain or let it pour, what difference does it make? Life depends upon the happy attitude you take. So what if your friends all turn you down? Wear a big smile and bow. Maybe we won't be here too proud 100 years from now.
You know, Mary, this is the best New Year's Eve party I've ever been to.
Me too.
Where's Phil?
You're standing on him.
How do you like that?
Well, it's Don's fault. He shouldn't have let him drink so much.
What do you mean, Don's fault? Phil was this way when he got here.
He was not.
Mary, when Phil arrived, I opened the door and he fell in like a body and
We're all jolly boys.
Yeah. Hey, listen, it's midnight. Let's have a song. The old acquaintance be forgot.
Well, not a bad idea. I'll give the old
Well, tonight the old year goes out and the new one comes in. Let's all hold fate for this new year that the way for peace will be found. But if not found, let America be strong and not be found wanting.
Okay, let my class be strong. I don't know how many of you are still there, but let me end the stream. I'll see you still next week for the last exam. Okay, see you next week. See you next year.